Okay, hi everyone. Good morning, good afternoon, good evening, good night. Welcome to another MIT Innotherm. If you could go to the next slide, Dan. So we're very excited today to share with you a distinguished panel of speakers focused on the opportunities in nano-engineered surface designs. Professor Dan Preston at Rice University will be the moderator for this session. He was a postdoctoral fellow at Harvard University with George Whiteside, and he did his PhD in mechanical engineering at MIT. His research areas of interest are in energy and thermal sciences and materials and engineering, as well as fluids and fluid mechanics. So it's a great pleasure to have Dan here to introduce the speakers of our panel.
Great. Thanks, Evelyn, for the introduction. I'm excited for this session as well and grateful for everyone who's able to attend. Looking forward to some of the discussion here from our speakers, which include Dr. Dimos Poulikakos, currently a professor, ETH Zurich, as well as the chair of thermodynamics and the head of the Energy Science Center. He's been recognized with several awards, including the Max Jacob Award and the Nusselt Reynolds Prize. He's interested, as we'll see, as a common theme among all of our panelists today, in both interfacial phenomena and wettability, and also in energy and thermal related applications. So excited to have Dr. Poulikakos here today. We'll also be hearing from Dr. Doris Vollmer, currently the group leader at the Max Planck Institute for Polymer Research. And she's also a professor at the Johannes Gutenberg University of Mainz. She's known for a lot of work lately in slippery lubricant impregnated surfaces, and in fact is on the steering committee related to these soft, flexible, and adaptive surfaces. And as I mentioned, we'll see a great expertise both in interfacial phenomena and wetting, as well as in energy related applications like CO2 capture and storage, from Dr. Vollmer. Next, we'll be hearing from Dr. Jas Takata, currently a professor in the Department of Mechanical Engineering at Kyushu University, and also an honorary professor at the University of Edinburgh. Dr. Takata is the president of the Heat Transfer Society of Japan, and also the president of the Japan Society of Thermophysical Properties. Has been recognized with numerous awards throughout his career, and looks at research areas again that cover energy related applications. So things like heat transfer enhancement, looking at areas including boiling and condensation. Also then looking at how to improve these areas of heat transfer using interfacial phenomena and wettability based techniques. And then the fourth and final panelist that we'll hear from today is Dr. Nenad Milkovich. Dr. Milkovich is currently an associate professor at the University of Illinois Urbana-Champaign in mechanical science and engineering, with courtesy appointments in electrical engineering and materials research laboratory, and also serves as the associate director of the Air Conditioning and Refrigeration Center. Dr. Milkovich has been awarded with the NSF Career, the Office of Naval Research, YIP, among other awards, and is probably best known for work in condensation, and also works in other areas of two-phase heat transfer using techniques that are based on wettability and interfacial science. So we see that all four of our speakers and panelists today share this strong background both in interfacial science, surface science and chemistry, and then using that and leveraging it to improve heat transfer, particularly looking at phase change heat transfer in a lot of these applications. Some of the specific applications where micro and nanoscale engineering of surfaces can be useful for thermal and heat transfer applications include these four common areas that many of you have heard of: radiation, evaporation, condensation, and boiling. And so in the top left, we see some photonic design of a surface to get subambient daytime cooling. Looking at evaporation, we find that we can design surfaces at the micro and nanoscale to improve membrane-based desalination, shown by some of the results here. In condensation, using something like a super hydrophobic surface in this example to decrease condensing droplet departure size and improve heat transfer performance. And also looking at boiling. So on the flip side of the coin, typically seeing superhydrophilic surfaces that improve things like the critical heat flux, the maximum heat flux you can achieve before a practical failure of the boiling surface. And so today we'll be focusing primarily on nano-engineered surface design for phase change heat transfer applications, although it's worth mentioning that there's some really promising work lately combining radiation and some of these phase change heat transfer mechanisms together using nano-engineered surface design. And in fact, we'll hear from some of that from our first speaker, Dr. Poulikakos, for some of his recent work. To give a little bit of background before we jump into the talks, I'd like to talk about how you can control wettability and start with the definition of how can you even quantify wettability. And you'll hear this term come up a lot, the contact angle. So the contact angle for a droplet in this case is defined from the liquid solid interface to the liquid vapor interface through the liquid itself, theta here. And we find that the droplet can take many different shapes and contact angles in what we would call a partially wetting regime, ranging all the way from super hydrophobic surfaces with very high contact angles, also called super omniphobic or super oleophobic for fluids besides water, all the way down in contact angle to super hydrophilic or super omniphilic surfaces. So these are surfaces where the fluid has a strong affinity for the solid and will spread completely over the surface. And so this is great in terms of an area, a design space that we're able to tune the wettability of fluids and their interaction with solid surfaces. But how can we actually do it? The design space consists of two primary areas of inquiry. The first being the chemistry of the surface itself, which would be at the atomic or molecular scale. And so the example shown here compares water on silicon dioxide to water on Teflon, in both cases a flat surface, and we see a stark difference in the observed contact angle. The other area or the other aspect or design space that can be tailored is the geometry of the surface. And so we can see that that's tunable at both the micro and nano scale, including applications that occur in nature like the lotus leaf, surfaces that can be designed, for example here, micropillars that were made in the clean room, and then also surfaces like these nano metal oxides that can be formed with simple, scalable, wet chemistry-based processes. And so now finally looking quickly at where are these tailored surfaces in use and where can you tune the wettability for certain applications? Well, first of all, thinking back to the lotus leaf, it's observed commonly in nature's own design. It's also useful for applications like waste reduction, in this example for a lubricant impregnated surface from the Varanasi group, and also in fluid repellency, looking here at a super hydrophobic surface on which droplets coalescing at the microscale will spontaneously depart from the surface. And then looking more at applications related to thermal and heat transfer areas, thermal management is a critical application, thinking about things like heat pipes, where either boiling or evaporation and condensation must both occur. Thermal management is critical for high heat flux applications, for example, very high powered electronics systems. Steam cycles are another critical area that represent about 70% of all electrical power generation worldwide. And thinking about the boiler and condenser present in every steam cycle, we identify that this is a critical area in which we can use tailored wettability to improve heat transfer performance and therefore improve electrical power generation efficiency. And then the final application that I'll call out and that we'll hear more about in our first talk today will be ice prevention and shedding, very important for aerospace industry. So following that brief introduction of today's subject matter, I'd like to get to know the audience a little better. And to do that, I'm going to administer two polls right now. The first poll will be, oh, looks like the results of the first poll are already shown here. So, oh, the first poll has been relaunched. So we'll give people a moment to indicate what do they consider to be their area of expertise so that we can get a feeling for how much background our speakers should give versus how much detail and specifics related to their science and applications they should go into. And so it looks like the poll results have stabilized, and so I'll end the poll here. And we find that 65%, the majority of our attendees, actually do consider their area of expertise to be either interfacial phenomena or phase change heat transfer. So I'm excited to see that we'll be able to get into some of the specifics, some of the nitty gritty here with our discussion. The next most popular response was that people do find a significant conceptual overlap. So looking forward to some nice technical discussions that maybe get into the fundamentals a little bit. I'll move to the next poll. And this poll tries to gauge what level of technology readiness are people interested in. So let me move to poll 2, which has just been launched. And seeing now that the results are stabilizing, I'll go ahead and end our poll. Looking at the results, we find that around 70% of our attendees today are interested in things at the laboratory scale, with the runner-up here, 25% being interested in the first step in terms of translation to an industrial relevant environment. So again, thinking that we'll be able to get into some really nice fundamental discussions, and then thinking about how do we translate, how do we get these surfaces to the next level as well. With that, I'll introduce our agenda. We'll have about 50 minutes for the presentations. There'll be about 12 minutes each, and we'll follow up with some discussion with the panelists for about 30 minutes, after which we'll wrap up. I would like to point out that you are able to submit questions using the Q&A button shown on the slide here, which is available in your Zoom program. We'll be pulling the questions from that stream. You won't be able to see the questions as attendees, but you will be able to hear me ask our panelists and facilitate the discussion. Please also go ahead and submit suggestions you have for future topics and speakers, and the meeting will be and continues to be recorded. So with that, what I'll do for now is stop my screen share, and we'll have Dr. Poulikakos as our first speaker go ahead and share his slides. And it is coming through. Looks like you're ready, although you are on mute.
So, can you hear me now?
Yes.
Thank you very much. So I'm hitting my timer, and I'm starting. Thank you very much for the nice introduction, and I'd like to also thank the organizers, in particular Everly Wang, Professor Wang, for thinking of and organizing this colloquium. I'm very happy to be here, and I'm very excited to be able to share a few thoughts with you on we talked about phase change earlier, on the topic of freezing, frosting, some of its physics, and how then we can use some of this physics to inform the engineering of surfaces for its passive mitigation. Freezing and frosting are phenomena that need no introduction. I have a bunch of pictures here. One of my favorites is this with black ice, I assume in some kind of highway in Nebraska. So I'm not going to speak too much about the motivation of this work. It is related usually to unpleasant phenomena, from catastrophes to annoying phenomena, and by that I mean fogging, and then frosting that may come after it. But what is also true is that freezing and generation of ice, and I'm talking about water today, are also very beneficial to humanity. Think of the benefits that we've derived also out of ice in the food industry, food transportation, medical industry, and so on and so forth. Also, our pleasure. I mean, most of these soft drinks would be really undrinkable without ice cubes. So it is a very complex phenomenon, really involving transfer fundamentals and interfacial science, surface engineering, as you will see, and of course, in addition to wetting and what you heard already, it involves nucleation of thermodynamics, because we do have a phase change phenomenon taking place during freezing. And I will discuss two topics today. The first one, I talked about physics, and I talk about exploiting the physics of the fact that freezing does not occur nicely at 0 degrees and at equilibrium, as we learn in the first course of thermodynamics at the university, but it takes place in nature and technologies just about every time from a super cool state, from a metastable state, and that comes with it, brings with it a number of interesting intrinsic phenomena, which then I will try to show you how one could perhaps exploit to ameliorate icing by generating intrinsically ice shedding surfaces, that is without electrical heating, chemicals, and so on and so forth. And I'm going to start with, I did see that about 60% of the audience have a background in the general area, but some 40%, that is significant, do not. So it is a good idea to give a little background on what we mean about nucleation and ice nucleation, with the simplest system possible, really, which is a droplet, as you see here, sitting on a surface. And as the temperature is decreased, goes to 0, even below 0, then of course one can observe the tendency of water molecules to form ice, small crystals, embrya, or embryons, depending on your preference. And of course, they can form this in the body of water, or if you have an impurity in the water, they will form this on the impurity, and that is preferable, as we'll see in a while. But of course, the biggest impurity we have in application, really, it is a huge impurity. It is the surface upon which your liquid rests, right? So really the role of impurity in most applications is taken over by the surface. And as you'll see in the next slide, I mean, these surfaces tend to help and accelerate ice nucleation. Now, these embryos, when they do not have an easy life. When they come to life and they start appearing, they're very small in size, and the growth, as you can see in this very simple energy size diagram, their growth is not favorable. Okay, so if they try to grow, they have to go up the energy barrier and overcome an energy barrier. But as they keep growing, and as a function of time statistically, you start having embryos that grow fast enough, reach a critical size that I show here, and then from that point on, the growth is favorable, that is toward decreasing energy, and it occurs actually explosively, extremely fast. Right? And of course, this barrier is a function of temperature, and the lower the temperature, the smaller the barrier. So you can reach the point at about -40 where there is no barrier, and every embryo will grow, right? But generally speaking, even at a temperature of -10, -15 degrees, you really have to wait for icing to take place, actually. On a surface, and at 0 degrees, this barrier is much higher. So effectively, you're going to have to wait a very, very long time for icing to take place at 0, and that doesn't really happen in reality because our temperature keeps changing. All right, so if temperature is falling in applications or in nature, and 0 never has a chance, right? We never stay at 0 for a very, very long time for the ice formation to take place at 0. It always occurs at a metastable state when the liquid is at temperature below 0. Right? Now, all that is for homogeneous nucleation, what I see, without the influence of a foreign body in the water. If you have heterogeneous nucleation, like the one I show here, that is if your liquid water is in contact with a foreign substance, like the surface, of course, this barrier is pretty much, according to nucleation theory, given by an equation that is similar to before. That would be the homogeneous case, times an interesting function here that is a very long function. I didn't write it theoretically. That is a function then of geometry of the texture of the surface, where r is not the RMS, but it is the radius of curvature of your texture, and theta is a wetting angle, and therefore both architecture of the surface as well as wetting properties play a role into determining this f. And of course, you know, this f has by its definition a value between 0 and 1. And if you wants to retard ice nucleation, one has to make, of course, this function f, which I do not show explicitly, as close to 1 as possible, so that the energy barrier would be as large as possible and ice will not form for as long as possible. So that, for a little bit of a background on ice nucleation, I want to add only one little thing. Then as these embryos are generated, of course, they release their latent heat. So it is a process where you have a very low temperature, embryos are generated, locally generate some heat, and life goes on, all right? So I will show you the result of a process like this in the next slide, where I have a droplet on the surface. We didn't do much architecturing on this surface. It is a barely phobic surface, I think. And now we have an environment, everything is at a low temperature, minus 15 degrees. And as you see here, the droplet is still at a liquid state, all right? And then we're waiting and waiting, all right, despite the minus 15 degrees. And then we observe the following. Boom, suddenly something happens. Those ice crystals that I mentioned, the embryos that I mentioned earlier, become stable and they grow explosively, all right? By growing, they release heat, all right? And then when they release heat, they heat up the droplet, right? And the droplet from minus 15, you will be amazed if you're not familiar with this, within milliseconds, all right? Because now you have a mixture of these ice crystals and liquid, goes to its equilibrium temperature 0. So within milliseconds, the temperature, which is in a cold environment of minus 15 degrees, reaches 0. And after which point, there is a second phase of freezing, the normal freezing. Now you have an isothermal freezing where everything is 0 and the freezing proceeds to the end. The first phase is adiabatic because this release of heat is so fast. So the time scales of heat diffusion for the heat to go away are much larger. So effectively, you have an adiabatic, very rapid phase, and then an isothermal classical phase, let's say, or more classical, that lasts about 1,000 times longer. Okay, so this is sort of the story of cooling. Now, with that, of course, the following comes, that the droplet, like I said, finds itself to be very hot suddenly in a cold environment and then vaporizes. So there's a vapor explosion taking place, which you cannot see here, unfortunately, all right? But what you can see, its manifestation a little bit, because this vapor, some of this will condense around the surface, and you will see, if you see carefully here, that this surface will be surrounded by what I call a condensate halo, right? Now, when we observed this a few years ago, we thought, you know, that's kind of interesting. We wish we were the first to discover it. We were not the first to discover, really, this phenomenon is called recalescence. Metallurgists in many countries, I have my colleague here, Professor Takata, I want to say in Japan, when they were making these swords, they knew things like that a long time ago. But we tried to exploit it to design surfaces so that which use this phenomenon, this explosive vaporization, to probably get rid the ice out of the surface as it forms, that is, by having a structure here that builds up a pressure that overcomes the capillary forces on the holding the droplet on the surface and kicks it away, right? So I have no time to show you details of how this is done, and we've done it, of course, at the laboratory scale and with upscalable techniques, right? I mean, I have a few references here. I will be happy to share them with you if you're interested. Right? I will, instead of telling you how we did it, I will show you an example of how this happens now on a nanoengineering surface of that kind. All right. Only now our cooling does not occur through temperature, but through the fact that we have our droplet in a low pressure environment, all right, dry environment. The droplet vaporizes, all right, self-cools to -15, -20 degrees, although I'm not showing it here, self-cools, and then suddenly this phenomenon takes place, and this vapor explosion takes place from all over the droplet, the top and the bottom, all right, and we've designed the surface so the following occurs. So you see the droplet, and here under the droplet, the force is very high, it deforms the droplet, all right? And then, of course, you see the de-wetting that takes place because the shell is asymmetric and kicks the droplet away, right? So with that, we were able to exploit this first level of the first phase of nucleation. One could exploit the second phase of nucleation as well, because here I have a similar situation, only the droplet, of course, does not go away every time. A lot of times it can stay on the surface, as you saw from the previous phenomenon. And if it stays on the surface, you can have a surface design that exploits the second part of the freezing process, which I show here. Now this droplet is on the surface, recalescence took place, and now the second phase comes, where you have effectively the shell from the outward growing inward and downward, and it pushes the droplet by itself, the ice sort of sphere out of the surface. So with that, I'm concluding sort of these thoughts that we have and some of the work we've done in this sort of interesting area. And with my time running, I'm very quickly moving to the second and last part of this talk, where effectively now we're looking at frosting, and we look at surfaces that are transparent, and we of course do not want to have frost or icing on them, but we want them to stay transparent. That is, we want to treat them, but we want the transparency to stay. And so effectively the recipe for this, looking at the physics of the problem, is not to, so if you look into the specular irradiance of sunlight, okay, you see visibility to the human eye has to do with the visible spectrum, which stops at about 800, let's say, all right? But a lot of the energy of the sunlight is contained in the infrared, all right? Almost 50% of the energy of the sunlight was contained on the infrared, and then we decided to see if we can design a surface that absorbs radiation selectively in regions. That is, it does not absorb well in the visible, and so the visible stays transparent, but absorbs very well in the infrared. And in that, if we do that, then of course we absorb the infrared to elevate the temperature of the surface, and we avoid nucleation for condensation or even then later on frosting. I'm running out of time, so I will show you only this that says even a little bit of temperature increase, yeah, it can make a huge difference, because the nucleation density of the nucleating phase on the surface is the product of two exponentials, where the 1 over temperature is in the exponent. So even 1 degree of difference can change the nucleation density by several orders of magnitude. So one doesn't have to kill themselves to overheat the surface. 1 degree, 2 degrees will make a huge difference. So I'm skipping the how we do it, unfortunately, in the interest of brevity. And I will show you only one slide, which is a film. So we did the surface, it's a photothermal meta surface. And then effectively we test it. And as you see, the control surface is on top with frost on top of it, and the meta surface at the bottom. We turn on the light, and you see the tremendous difference between the two surfaces, of course. After about 30-40 seconds, we have complete melting of ice on one side, and on the other side, actually, we go to several hundreds of seconds, 400 something, I think, and nothing happens. So it has a tremendous effect, all right? So I find that also very interesting, and I think one can do a lot more work taking into account some of this physics in designing surfaces that are transparent. Transparency is important, and mitigate frosting and fogging. Right? So I'm closing with this slide. I'm thanking my collaborators through the years. I put them there in order that they appeared in the lab. And I'm clarifying at the bottom that this is not Sauron's eye from the Lord of the Rings, but instead it is light breaking through frost on one of our surfaces. Okay. Thank you.
All right. Thank you for that talk. And then I think up next we'll have Dr. Vollmer. So if she could share the screen, and I think then we'll also save the panel discussion for the end, as I mentioned at the beginning today. And so I can see the screen, but not get the audio yet. I think you may still be.
Yes.
Oh,
okay.
Great.
Okay, fine. Great. I also like to thank the organizers for organizing this meeting. And I'm happy to present part of our work on superamphiphobia membranes for enhanced carbon dioxide capturing. The increasing concentration of concentration of carbon dioxide in the atmosphere is intensively discussed during the last few years. It is well known that the carbon dioxide concentration in the atmosphere is not constant, but that it changes in course of years. What you see here is the variation of the carbon dioxide concentration during the last 400,000 years. During the last approx 200 years, we observed a strong increase in carbon dioxide, in particular during the last 50 years, related to industrial revolution. People are discussing carbon dioxide in the atmosphere a lot, all politicians, companies, but also people in society. Still, the carbon dioxide concentration increases steeply. Here, what you see is the average and also the seasonal variations. Carbon dioxide causes a problem because it absorbs IR light reflected from the Earth and emits part of the absorbed energy as heat, causing that there is this increase of the global temperature, here presented in the well-known warming stripe, where dark blue presents cold periods and dark red present warm periods. Aiming for the 1.5 degree goal, one needs to keep in mind that this implies that on Earth it's much more than on sea, because sea absorbs heat or heat better. Okay, CO2 is still, I think, a little bit an abstract concept. Therefore, I like to ask you to think about how much carbon dioxide is produced if you burn 1 gallon of petrol. Do you produce less than 1 milligram, 10 milligram, 10 gram, 10 kilogram, or more than 10 kilogram? Thinking about, for those not used to gallons, 1 gallon is equal to 3.8 liters. Okay, I like to continue. Actually, it's approximately 10 kilogram. So why? Oh yes, you see, so quite spread. Thanks a lot. So petrol primarily is composed of carbon chains. And if we heat, then we can break the bonds between carbon and hydrogen. And now the hydrogen can react with atmospheric oxygen to form water. The carbon can now react with atmospheric oxygen to produce carbon dioxide. Oxygen is much heavier than hydrogen, and therefore we observe a strong increase in weight. So the molecular weight increases, roughly speaking, by a factor of 3. So taking into account also the density of petrol, then we end up with a weight of approximately 10 kilograms. Thinking that 1 gallon of petrol produces 10 kilograms of carbon dioxide, we realize how huge the problem is also to store this if we want to store. On the other hand, what I think is even more important is with burning 1 gallon of petrol, we produce 22 times 10 to the power of 24 carbon dioxide molecules. As you can imagine, it's very tricky as soon as they are released to capture those again. Therefore, there is intense research in academia and in industry to find new improved capturing strategies. Typically, it's done going for aqueous alkanolamine solution. So then you have a bottle and there you bubble carbon dioxide into it. We were thinking about whether one can also go for membrane technologies, because membranes, they are modular, easy scalable, compact, and therefore maybe we get a process intensification. That is what we did.
One strategy to capture carbon dioxide is to make use of gas exchange membranes. Here, an amine solution flows over a porous membrane. This solution can bind carbon dioxide. The CO2-containing waste gas streams across the other side of the membrane. Most importantly, gas can diffuse through it.
However, we have some problems. So, amine solution easily wets the membrane. This greatly reduces the contact area between the amine solution and the carbon dioxide containing gas. Furthermore, amine solutions are quite aggressive because they have a huge pH. Therefore, they can destroy the membrane, and we can have clogging of the membrane, also reducing mass transfer. And therefore, we wanted to investigate the concept of superamphiphoric coatings. As already mentioned by Dan, superamphiphoric coating requires surfaces containing overhangs and fluorinated, and they are characterized by a huge advancing and receding contact angle, and the droplet rolls off as soon as we tilt the surface by, roughly speaking, 10 degrees. And this holds for both aqueous and non-aqueous liquids. So now we designed membranes having the idea that now the liquid can stream on one side of the membrane and gas at the other side of the membrane. We went for commercial polyester membranes. Here you see them at different magnification. So just they are composed of fibers. And then after treating, then at low magnification, the membrane appears unaltered. However, if you go to higher magnification, then you see that now they are coated with these kind of nanofilaments. How did we do? We placed our membrane, so our this textile membrane, into a solution of containing trichloromethylsilane in toluene in the presence of tiny amount of water. Then we have an hydrolysis and condensation reaction, and the filaments grow on the textile. Without further treatments, the surfaces are hydrophobic but not super amphiphobic, because we have methyl, and therefore we exchange the methyl group by fluor groups. And thereafter, as you see here, the amine droplets as well as hexadecane droplets, nicely rest on this surface, forming nice particles, and they roll off as soon as the surface is tilted a little bit. For comparison, we investigated polypropylene membranes. Here, commercial ones with 200 nanometer average pore size and 75% porosity. Teflon membranes with 220 nanometer average pore size and 85% porosity. And Teflon membranes having even larger pore sizes. Here you see, if we now place a droplet of hexadecane on our superamphiphoric surfaces, you see that we have a huge contact angle. And the droplet does not stick, but it easily moves over the surface. Contrary, on the hexadecane surface, the droplet wets, hexadecane wets the Teflon. So we observed a strong increase of the repellency of the surfaces compared to conventional membranes. How do we quantify now the carbon dioxide uptake? Therefore, designed the following exchange chamber. Here we have our amine reservoir, an infrared spectrometer, where we can monitor the binding of carbon dioxide to amine, and the solution is pumped, and here is the exchange chamber, and so that it's then back in the reservoir. So carbon dioxide binds to amine solution by forming bicarbonates. At a higher magnification, our exchange chamber looked like that one. So we have here our amine solution flowing over the membrane. Here is the membrane, and at the lower side of the membrane, we have our carbon dioxide. Now, because of the air cushions, now the carbon dioxide can easily diffuse through the membrane into the amine solution. To see whether that really worked, we measured the concentration, but first I like to show you how the setup looks like. So this one is our reservoir, the spectrometer, the pump, and our exchange chamber. Then we quantified the carbon dioxide uptake in course of time, and after approx 2-3 hours, depending on the volume of our amine solution, we observed a saturation, and even more important, just even after 50 hours of continuous operation, we did not observe a change in adsorption efficiency. That is supported by SEM images. After 50 hours, the surface looks unaltered. Then we were able to compare our results with the superamphiphoric membranes compared to the conventional membranes. And after 1 hour of exchange, we had an increase of carbon dioxide uptake by approximately 20% compared to the conventional membranes. And apart from this 20% uptake increase, we did not observe a decay over 20 hours. With that, I like to summarize.
To prevent wetting of the pores, we develop membranes with super liquid repellent properties. Thus, significant performance increases can be achieved to make carbon dioxide capture more efficient.
I was first very happy when I saw this, that we had a significant increase of carbon dioxide uptake. However, then we realized that this one is actually not the most important step in the problem. The huge step is that one needs to release in the carbon dioxide from the amine solution, and that requires heating to more than 100 degrees, typically to 110, 140 degrees. So the energy demand required to release this carbon dioxide and to compactify it boils down to reduced efficiency, for example, of coal power plants by approximately 20 to 25%. Second problem is that we have the storage problem. Now, what do we do with the captured carbon dioxide? We can try to store it in deep geological formations, exhausted gas oil fields, saline formation or stuff like that, or we can think about storing it as stable carbonates. The problem is we lack experience and therefore we do not know what the safety issues. From that point, I think we have only the chance to go for renewable energy, and we need to change our personal habits. With that, I like to thank Florian Geyer, Hans-Jürgen Butt, Clarissa Schönecker, Maria da Kunzi, and I like to thank you for your attention. And I think that we need to act now.
Great, thank you. And up next is Dr. Takata, who is sharing his screen now.
And thank you very much, Dan, for your kind introduction. Thank you for the organizers, everyone, and Ganchen, and for the MIT members. So today I'd like to talk about the mixed wettability surface for nuclear boiling. Especially, I'm focusing on the onset of nuclear boiling. And I talk about the water boiling and the ethanol boiling, okay? So these are the, my collaborators, Dr. Shen and Professor Takahashi and Dr. Hidaka, and the engineers from the USCJ companies, and also these students involved in this project. And this work is mainly supported by NEDO feasibility study program. Okay. So why I'm interested in onset of nuclear boiling? It's very important for the electronic cooling. So the boiling textbook says, you know, for onset of nuclear boiling, we need surface superheat. Okay. So in the boiling curve, yeah, I'm focusing on this onset of nuclear boiling. So here I showed the picture of the photograph of the loop heat pipe for the electronic cooling. So when the electronic device is switched on, temperature of the device goes up, but boiling doesn't start. And here, so when the temperature increase and reach it to the surface, sufficient temperature, then onset of boiling starts. As you know, the boiling has a higher heat transfer coefficient. Therefore, device temperature goes down when boiling starts. We call this temperature difference as overshoot temperature difference. The problem is if the temperature limit of the electronic device is like a green line, so it's before the onset of nuclear boiling, so the device will be damaged. Therefore, we'd like to have a lower onset of nuclear boiling temperature. Okay. We know how to decrease superheating at onset of nuclear boiling. One method is to inject, you know, non-condensable gas in liquid. Okay, so if there is a dissolved air in the liquid, so we have a lower onset of nuclear boiling. The other thing is wettability control. So hydrophobicity works, you know, in this case. So especially the for the electronic cooling case, So if we use water as a cooling fluid, so we need to have a boiling at subatmospheric pressure, which makes heat transfer works. Okay. So I summarize the effect of wettability on boiling curve. It's a typical boiling curve for the water. For the hydrophilic surface, as Dan introduced in the introduction part, so we can enhance the critical heat flux and also the minimum heat flux point to the higher temperature, okay, or higher heat flux. But disadvantage is the onset of nuclear boiling becomes at higher superheating. Okay. For the hydrophobic surface, so we can decrease the superheating at the onset of nuclear boiling, and also we have the excellent nucleation site, and we can enhance nucleate boiling. But another disadvantage is the CHF becomes lower. Okay. So therefore, we have prepared some, the wettability mixed surface like this. So for the hydrophobicity, so which elevates the critical heat flux and hydrophilicity elevates CHF, and hydrophilicity enhances the ONB and high heat transfer performance of nuclear boiling. And it works even in the subatmospheric pressure. This graph shows the result of the nuclear boiling at atmospheric pressure and low pressure. And also we can improve the onset of nuclear boiling. Okay. So next slide shows the movie. So as you see, now it's a atmospheric nuclear boiling of the plane Kappa surface. And but if you decrease the system pressure, for instance, 13.6 kilopascal, which is equivalent to 52 degrees Celsius in saturation temperature. So the bubbles is produced intermittently, and heat transfer coefficient becomes very low. Okay, like this black dotted curve. For the mixed wettability surface, we can enhance the nuclear boiling, and also we can improve the onset of nuclear boiling. For the especially in low pressure cases, okay, you see the boiling behavior is similar to that of the atmospheric pressure, and you see the similar heat transfer performance, okay, in both cases. So far, so we have been made experiments using the water, but we can obtain the new coating surface, halloysite nanotube coating, which has a higher contact, which shows a higher contact angle for ethanol. Okay, for the plane surface of the Kappa surface, so the contact angle is around 30 degrees. But for the HNE coating, so we have 100 degrees for the contact angle. So this coating material is synthesized by my colleague, Dr. Ma, and Professor Takahara's group, okay, in chemistry. So then we use this coating stuff on the Kappa surfaces, like we used in water boiling cases. And this is boiling feature on the this surface. Okay. So then this is a boiling curves for this surface, and we tested several spot diameter and spot pitches. Okay, and found the optimum combination, like a 2 millimeter in diameter of the spot size, and also the 5.5 millimeter in spot pitches. Okay, in these results, you see that if we do not have the HNET coating, the surface superheating at onset of nuclear boiling is around 220 Kelvin. But if we use that coating, so we can decrease significantly the onset of nuclear boiling, like as maybe 13 Kelvin. Okay, so this result was published in Applied Thermal Engineering. So the first author is my collaborator, Dr. Shen at the University of Tsukuba. And the next topic is the aluminum surface. Because the aluminum is very light, and it's very suitable for the mobility use. Okay, and it's easy to making the nanostructures by anodization. But maybe, as you know, that the combination with aluminum surface and water is terrible. Okay, so boiling we using the water, so make corrosion on the aluminum surface. Therefore, we tested this aluminum surface with ethanol, and also the anodized. We prepared the anodized surface, which is supplied by my collaborator, USCJ company. Okay. This company is aluminum, big aluminum company in Japan. Okay. So we prepared some anodized surface. One is a sulfuric acid anodized surface, and this one is a PAA is a phosphoric acid anodized surface. So the pore surface, pore sizes in both cases are different, but 10 to 20 nanometer, or this PAA surface has a 200 nanometer. The other Ka treatment surface, I don't talk about this because it's a different surfaces. And also, we use the HNE coating on top of these two anodized surface. Okay. So this is a boiling feature on the with HNE coating, and so boiling starts in a low superheating. Okay, but for the without HNE coating, so this in this case, the boiling occurs at a very high surface superheating, 56.7 Kelvin, higher than saturated temperature. And when the boiling occurs with HNET coating, so that you see the very the small bubbles departing from the this surface. Okay, okay, this is compares the boiling result with HNET coating and without HNE coating. Okay, in both cases, when boiling occurs, the boiling characteristic on the both anodized surface has a similar, almost the same nature, but the different thing is onset of nuclear boiling. Okay, so by HNET coating, we can decrease the onset of nuclear boiling surface superheating from 54.3 Kelvin to 13.1 Kelvin. It's a significant improvement. Okay, so this is the last slide on my talk. So for water, so we first use a Kappa surface with mixed wettability patterning, and this surface decreases superheating at the onset of nucleate boiling, and also the enhances nucleate boiling under subatmospheric pressures. For the ethanols, so we used halloysite nanotube HNT coating on Kappa surface first, then it decreases significantly the onset of nucleate boiling temperature. For the anodized aluminum surface with HNT coating pattern enhances the nucleate boiling and also decrease the surface superheating at the onset of nucleate boiling. Okay. So for the future work, so we started from water, and now we are testing the ethanol. So we expand this technique to the other fluids. But the problem is how to find a coating substance for wettability contrast. So this is the end of my talk. Thank you very much for your kind attention.
Great, thank you. And up next will be Dr. Milkovich, who has just started sharing his screen. So I'll let him get into it.
Okay, that's full screen, right, Dan?
Yep, looks good.
Okay. Thank you, Dan, for the wonderful introduction at the beginning, and thank you, Evelyn, for inviting me to be on this great panel. I'm going to open my talk today with a question. Where can we use nano-engineered surfaces? I think a lot of the previous speakers have motivated this topic well. My talk today is going to focus a little bit more on thermal applications, mainly icing, electronics cooling, petrochemical separations, manufacturing or scale up for HVAC and R applications in building energy, and then also enhancing manufacturing processes like brazing. Nano-engineered surfaces have many opportunities. There's massive economic opportunity, demand from industry to actually utilize some of the quoted enhancements that have been published in literature. They offer new routes for compact and high performance single phase as well as two-phase heat transfer enhancement in devices. And nano-engineered surfaces offer methods to handle what I call tertiary problems in heat transfer, such as icing, frosting, fouling, corrosion, manufacturing. Some of these have already been touched on by the previous speakers. But in order to get us there, there's a few fundamental challenges that we have to overcome. There's relatively few demonstrations of working devices and systems using nano-engineered surfaces. There's a lack of software and design tools for structures. There's a lack of durability measurements in real application settings. They have been demonstrated quite a bit for water and for steam, but there's limited work on dielectric fluids as well as refrigerants. And there's a lack of scalable manufacturing methods that could be used for legacy as well as new additive manufacturing techniques. So in my talk today, I'm going to discuss a little bit about durability of nano-engineered surface designs, which we focused on in my lab. I'm then going to touch on a few different applications and spaces where we have developed high performance heat transfer devices using nano-engineered surfaces. And lastly, I'm going to come back and talk a little bit about scalable nano manufacturing and what we could do to get us to that next higher TRL level. So one of the most well-known and studied nano-engineered surface durability challenges, and Dan touched on this in his motivation in the beginning, is in dropwise condensation. Dropwise condensation is a century-old process, which is currently not used in any application really, mainly due to durability issues of the thin promoter film, which has to be placed on the metallic surface. So if you are to observe dropwise condensation using optical microscopy, what you'll see forming are these water blisters, which could actually take your nanoscale film, remove it from the surface, and delaminate it. Now, one thing we've been doing in my lab is using atomic force microscopy, scanning probe, and nano indentation techniques to really study why is it that these films delaminate and what really governs their degradation, such that then we could work with chemists and material scientists to develop better coatings. And so using principles of wetting as well as mechanics, thin film mechanics, we're actually able to develop theories and validate them to predict how durability is impacted by both the processing as well as the material properties. And so I'm showing you this parameter down here, omega. The red is criteria related to pinholes, which are key to durability. And the blue are parameters that are related to the film properties, E being the Young's modulus, G being the wet adhesion, and H being the thickness. And so using this fundamental understanding, we're then able to design regime maps to tell us where we lie and where we need to be for durability. And what we find is that for enhanced dropwise condensation, for long-term condensation, we need pinhole-free coatings. We need high wet adhesion, high Young's modulus, or a high thermal conductivity such that our thickness can be elevated. So we could come at this problem from two avenues. If we want to tackle the pinhole parameters, we've been working on developing self-healing Vitromer nanofilms. This is in collaboration with Christopher Evans in material science. These are PDMS-based PFC-free polymers that are self-healing due to exchange of network strands. What ends up happening is you could have exchange in spatial locations of bonding, which enables the self-healing. And one thing that we've been doing with Chris and his students is actually developing the manufacturing paradigms to actually make these Vitromers into nanoscale films. We then take these and study them using atomic force microscopy, and we could indeed show that pinhole density can be drastically reduced. And even if we induce pinholes via nano indentation, they could be removed. And then finally, by inducing pinholes with nano indentation, these rectangular arrays, we could actually compare our Dyn PDMS films with CFX fluoropolymers, which are just your standard state-of-the-art film. And indeed, you see that for the CFX film, you form blisters, whereas for our films, they will actually self-heal and droplets will form on top. Now, if you want to come at the problem from the material standpoint, we've also been looking at enhancing those material properties which are mentioned by developing multi-layer fluorinated diamond-like carbon. We use multi-layer because it gives you the functionalities that are required to get you to the material properties that you need. In this case, we use titanium interlayers for great wet adhesion. We use different compositions of DLC layers to give us thermal stability. And then we have a bulk layer on top of co-deposited fluorinated DLC, which gives us our low surface energy. And indeed, if you plot the nano indentation curve, the load as a function of indentation depth, you see that for FDLC coatings, your Young's modulus, it has inorganic-like behavior. So it's much stronger than a typical CFX amorphous fluoropolymer. And if you then do tests of abrasion and you plot the contact angle as a function of abrasion cycle, you clearly see much greater durability when compared to state-of-the-art coatings, nano-engineered surfaces. So in this case, we could go all the way up to 5,000 abrasion cycles using a diamond tip while still maintaining dropwise condensation. We then characterize the heat transfer performance, and by developing systematic experiments that could be run for a long time, we're excited to say that we've been able to demonstrate these coatings on a variety of different substrates for timescales on the order of 3 years at this point. So you may ask yourself, well, is dropwise condensation really the only application for these thin nanoscale films? And my answer to you is no. Another really high potential application is actually in electronics cooling. And Doris touched on this a little bit with her CO2 motivation. Data center cooling, power electronics, data centers are becoming a major draw of electrical consumption within the United States and across the globe. And so one thing we've been thinking about is, can we use these thin, durable polymer films as voltage standoff to limit leakage current, coat our electronics directly, and then enable direct immersion cooling in water. And it's a huge advantage, mainly because current immersion cooling techniques use dielectric liquids, which suffer from very poor thermophysical properties, low CHF, and high resistance from junction to fluid. And so what we do is we monolithically integrate on electronic devices made from gallium nitride. We then integrate these into a 7 kilowatt, 600 volt DC-DC boost converter, which we obtain with our collaboration with Robert Pilawa. We coat it with Parylene C, and indeed, we're actually able to dunk it in water and run it at full power for days on end without any degradation. And what you see down here is actually the power dissipation per device, as well as the heat flux per device as a function of delta T for a range of different fluids. And you'll notice that the Novec dielectric fluid, which is a common immersion fluid currently used, can really get you only on the order of 35 watts per centimeter squared. Now, if you were to shift to water with a thin enough Perylene coating, you could reach all the way up to 350, which has huge implications for power densification. So from this point, we've moved on. And what we're currently doing now is taking it a step further and actually coating on top of our Perylene copper directly via electrodeposition. And so now this brings in a new paradigm of directly depositing or printing your heatsink material right on your electronics, removing thermal interface materials, and really allowing high heat flux performance for some of these high power devices. Now, shifting gears a little bit, I talked a little bit about the need for work on refrigerants. One area where we have a lot of interest is in building energy applications where refrigerant flow boiling is a huge need. Takata Sensei actually discussed boiling and motivated it well. He even talked a little bit about current boiling techniques where we typically use nano-oxidation coatings, for example, boehmite. Now, one of the issues with using boehmite is the fact that durability concerns arise. And this mainly stems from the fact that when you form a nano-oxide or a nanoscaled oxide on top of a metallic surface, you're forming a distinct interface. You have different coefficient of thermal expansion mismatch, and hence you actually induce failure mechanisms via delamination of the structures. The way we've been overcoming this by developing durable surfaces is by using crystallographic etching of metals. What crystallographic etching allows you to do is to have a nice uniform metallic composition of the structures that matches your substrate, which is shown by the schematic down here. It also allows you to range the structural length scale to get it to the point where nucleation flow boiling is enhanced, and you could see an enhancement. So by doing rigorous heat transfer quantification, here we plot the flow boiling heat transfer coefficient as a function of heat flux for 3 different mass fluxes. We see that if we use the conventional nanoscale boehmite surface, there's no difference between the bare. But if we use our aluminum etch surface, we're able to demonstrate on the order of 3x enhancement. There's a very minimal pressure drop penalty, and 28-day durability tests indicate good durability of our structures, although more work is needed. And so where we are now is we've demonstrated these surfaces on low fin tubes, which are commercially available, because we want to demonstrate them on highly corrugulated internal channels, and we're really pushing this work forward for industrial implementation. Now, Demos did a great talk on icing. One area where we've had contributions is looking at scale up of passive anti-icing surfaces. So these are a little bit different from what Demos discussed. Dan discussed this a little bit in the beginning, where we use coalescence-induced droplet jumping on super hydrophobic surfaces to actually remove supercooled droplets from the surface before they could freeze. There's been a plethora of wonderful work from many different groups all across the community. Where we have really been making inroads is thinking about how do we now scale up these surfaces and apply them to real heat exchangers, as shown down here by a commercial heat exchanger provided from Braceway. And the way we do this is we develop cleaning, nanostructuring, and atmospheric pressure functionalization paradigms to then be able to actually put these on large-scale heat exchangers and really quantify what is the advantage, what would be the advantage in a real system setting. So we then instrument these both either in quiescent and in wind tunnel conditions. And we can then clearly demonstrate the enhanced performance and delayed de-icing when compared to a bare heat exchanger on the order of 3x delay in terms of time. You could also see this down here with the heat transfer rate as a function of time. For our super hydrophobic heat exchangers, we really maintain this high heat transfer rate simply because we keep the frost off the surface for longer. So where are we now? We've been working with a company called CTS, which is here in Urbana, run by Professor Pega Hrnjak, to actually demonstrate this in third-party validation at the company on a Modine gas cooler for electric vehicle applications. And that's what you're seeing here on the left. This is our super hydrophobic coated microchannel aluminum heat exchanger. This is our uncoated heat exchanger. And what you see is if you plot the heat transfer and pressure drop after integration in a transcritical CO2 heat pump cycle, you clearly see the advantage of super hydrophobic coatings compared to bare surfaces or even super hydrophilic nanoengineered coatings. Similar with pressure drop. And so what this translates to after rigorous quantification is that the COP we obtain with our coated surfaces is 2.1 when compared to 1.5 for a bare heat exchanger that can't delay frosting. And just this is my last slide. I want to touch a little bit about manufacturing. There's been a lot of interest. There's been an Inotherm talk, which was great on additive manufacturing techniques. One area where we have a lot of work is actually looking at how do we now develop nanostructuring methods for alloys which are used in additive manufacturing. As you know, many of the alloys that you have to use in additive aren't used currently in manufacturing processes, for example, AL6061. So we have to use things like aluminum silicon. And interestingly, it turns out that some additively manufactured materials give you better opportunities when compared to conventional materials. So for example, if you use crystallographic etching, you could see that you have these cellular-like honeycomb structures that form on the surface. These are actually really good at preventing liquid propagation laterally and enhancing droplet jumping. And you see this here through the video. This is an additively manufactured tube, and this is the conventional tube. And you clearly see water shedding. It's just through the roof. And so what we've been doing now is combining topology optimization, additive manufacturing, as well as nanostructuring to develop these highly compact, monolithically developed single print condenser heat exchangers, which we can now use, remove fittings, and remove some of the integration penalties. And we're very excited by this work and think there's plenty of opportunity here. And so finally, I want to talk a little bit about some of the challenges and opportunities for our field. In terms of durability, degradation conditions and mechanisms vary based on application. There's a significant lack of rigorous methods and standards to assess durability, and there's a lack of mechanistic understanding on degradation. And although we've been doing a little bit of work along with a few other groups, there's massive opportunity out there for the community to really understand these fundamental problems and get us to that higher TRL level to develop better materials. In terms of manufacturability, the question I always ask is which nanostructure is best? There's a need for techno-economic analysis and design tools. And how do we integrate this nanostructure fabrication with legacy techniques as well as novel additive manufacturing techniques? In terms of working fluids, I talked a little bit about our work on R134A, and there is a little bit of work out there from a few groups on R134A. But the opportunity here is looking at some of these novel low GWP refrigerants and mixtures. There was a fantastic Inotherm talk by Professor Pega Hrnjak and Bob Lowe about some of these new refrigerants which are coming in. We need to do more work on characterizing nano-engineered surfaces and how they can enhance these fluids. And then design and analysis, right? There's a lack of software tools and design methods for engineers to use in companies to actually implement these in applications. And the last bullet I have here is on machine learning and artificial intelligence. They're very promising, and they could actually, they present a great opportunity for our field, but we have to keep an eye on fundamentals and move away from some of the classical black box techniques that machine learning and artificial intelligence are known for. So with that, I wanted to actually list a few papers which I didn't talk about that are related to the talk today. There's a lot of good work out there. So these papers are actually from my group. But to be a little bit more inclusive, I also list 3 great review papers on this field. The first one being on flow boiling specifically, and number 2 and 3 here actually being great topical reviews, one by Evelyn's group and one by a Midwest group, looking at micro and nano engineered surfaces for 2-phase applications. I also want to make sure I thank my collaborators. I work with some of the best people in the world, and so they really facilitate the work that I showed here. And the funding agencies, ONR, ACRC, POETS, as well as Eisner. And then it'd be a shame if I didn't mention the great students and postdocs that actually did the work that are shown down here. So thank you.
All right, excellent. So I guess I'll first suggest that we have a virtual round of applause for all the speakers. Thanks for talking about some of your ongoing work. I'll encourage also our speakers and panelists to come back into the room here for our panel section and turn their videos on such that we can facilitate some discussion. I'll also suggest to the audience that if you have any further questions, to go ahead and submit those now. If you'd like those to be answered, we'd be happy to take more questions. I guess I'll kick off with a question that we already got from the audience from a Dr. Nagayama, which is directed to Dr. Takata. Could you please explain the reason why your anodic aluminum substrates of different surface structures have similar boiling curves?
Honestly speaking, I do not have a clear answer about that. So, but the size of the pores, size of the pores for the 2 anodized surface are quite different, 10 times different. But once boiling starts, it works similar cases. That is, so from the nucleation theory, we cannot at this moment explain this reason. But it's a very good question. Okay. Sorry about that.
I might move to a follow-up, which came to mind for me, which is maybe you, Yas, and also Ninad could talk briefly about something Ninad mentioned, which is that he observes that the oxide-based coatings will sometimes degrade or delaminate due to this mismatch in the coefficient of thermal expansion. Is that something, Yas, that you have observed? Is that something that causes your coatings to degrade?
Mm.
Or Ninad, on your side, would you?
Yeah, maybe I can answer. So there's issues with CTE mismatch when you cycle the system if you're shutting it down and turning it on. There's also issues with particulate deposition. So sometimes you may have contaminants in your fluid, and then especially as you scale down to nanoscale structures, right, it becomes an issue where you could clog. And I think Evelyn's done some work on this, as well as others, through the DARPA iSchool system on evaporative cooling. And so classically, if you were to look at commercial grade, what industry would call structures, there already are tubes which they call tech tubing. Tech tubing has what looks like structures, but they're millimetric. And so many times you have to use millimetric structures simply because you can't maintain purity of the working fluid. It's a significant constraint depending on which industry you talk to. If you talk to automotive industry, they have a minimum fin pitch or minimum feature size they have to maintain. If you talk to a company like John Deere or Caterpillar, that fin pitch is even larger, right? Because they can't guarantee that people are putting coolants in their tractors and industrial equipment that are really pure. And so, yeah.
Gotcha. I'll follow up with another question from the audience, a little bit different direction, but just reading it here as submitted. It's an open question on liquid water. When it's confined in a porous structure, such as a porous polymer or carbon, it can have a much lower evaporation enthalpy than bulk water. What is the fundamental reason for the reduced enthalpy of confined water? If someone could address that.
I'll let somebody else take this one.
It seems to me maybe Demos could provide an answer regarding the...
Everybody is silent, so you go to Demos, right? So, well, I'll take a crack at this, as I'll take a crack at anything, really. So, first of all, how do you define it, all right? So, effectively, you're talking about, because in melting and freezing you have the same thing, or evaporation. If you have a confinement, your liquid is very different. It's dominated by wall effects, of course, the structure and the molecular interactions, than when you have it in a bulk state. And effectively, then if you define it in that the other phase, when you vaporize, because you have now the liquid phase and you have a vapor phase, all right? So how do you define the enthalpy of the vapor phase? Do you define it in the free space, or you define it also confined, all right? So I'm going to have to assume now that everything is confined with change phase in the same very small space. And if it is if the interactions are dominated by those wall effects, regardless of phase, that might be the reason why you don't have that much of a difference between the two. That's my guess, all right?
I'm not sure if anyone else had a follow-up on that. Does it sound reasonable to the panel, or if there's any discussion to be had?
I mean, I think that sounds very reasonable, right? Especially if you have a hydrophobic ore, which was mentioned, right? The intermolecular interactions are very different when compared to a hydrophilic one, or even the self-interaction with water. So just intuitively, I would think there would be a significant change. Yeah, I agree.
But it's only important, just roughly speaking, from length scale below, roughly speaking, 50 nanometer or even smaller. Otherwise, you have bulk behavior.
Of course.
All right, thank you. for that discussion. I have another question from an anonymous attendee in the audience. This question asks about the largest hurdle to developing durable coatings applied to industrial applications. So take that as a theme for the panel. Specifically, maybe we can have Ninad kick off. It says, such as steam surface condensers, is there a physical limit to overcoming pinhole deficiencies?
Yeah, so some of the work that we've been doing, and we've had a lot of interest in discussions with companies like Exelon that actually run coal or nuclear power plants. We've also had visits. We have a coal power plant here on campus, right? And so we can actually see industrial condensers. And in my view, there's two limitations. Of course, there's the fundamental one, right? Can we make steam condenser surfaces that could last for 10 years or 15 years, right? And really get us an enhancement. But I think a more prevalent one for coatings in general, the first one being, for example, for steam condensers, you're working with a highly conservative industry, and so they don't want to have down days. They don't want to install things where they may fail or they lose power. So the industry itself is very conservative to change, and that includes more than coatings. There's other thermodynamic cycle types of enhancements where they could boost efficiency, right? But the industry won't take them just simply because of reliability concerns. The second one is cost. And so especially if you go to like building energy technologies, you're talking about companies which make millions of products every year at the absolute minimum cost. And so if you want to implement a coating technology, it's not only the added value to the customer, you also have to simplify their manufacturing processes. And hence why I think there's a big need from the community to really look at enhanced manufacturing or enhanced nano manufacturing, not just to get these in there, but also to maybe use nano engineering technologies or processes to eliminate some current legacy manufacturing techniques. For example, tube expansion in heat exchangers, right? If we could eliminate that using electrode deposition, I think that's a fantastic idea. And so cost is another big barrier where, you know, we really have to work on that and work with the companies.
So I'm taking a look at the time. I know we just had some more questions come in. I'll reiterate that the questions that came in and haven't been answered, you can take a look at those on the YouTube channel afterwards. What I'm going to do is, because of the time, we're right at the end of the session here, I'm going to share my screen again with some closing information. So you should be able to see now that we'll have the next Inotherm webinar coming up in 2 weeks on May 12th. It'll be Dr. Ken Sandage at Purdue. And then to wrap up for today, I'd like to suggest that you type in your suggestions for future events, speakers, topics, and format. Please sign up for the email list, which you can access at the website. And you can also see all the prior Inotherm videos and Q&A that hadn't been able to be included in the panel discussion as well on this website. I'll stop sharing my screen. We'll wrap up for today. Thanks again to all the speakers and panelists for the discussion and their presentation of their work.
Thanks, everybody. Thanks for having us.
Bye.